Okay, good afternoon. I hope you had good rest. And today is the last day and last lecture. I hope you learned something. And of course, tomorrow is the exam. And you are going to, Dr. Sharma is going to say something about that after this is completed. So, anyway, let's go back to the lecture now. And this is where we stopped in the morning. I was talking about digital or numerical relays, and they have been since 1980s. The development started, and now they are the predominant form of relays that are used in the business. So one of the companies that produces those relays is Schweitzer Engineering Labs, and this is the company in United States, and they is a picture of what it looks like. And the advantage of digital relay is that it's a multi-function relay. You have all kinds. This is basically a computer essentially. So in the old days, when you had a mechanical relay or even static relay that has fixed function, but this one is a multi-function relay because all you have to do is select specific characteristics, and it's basically a computer. A few more devices. Load break switch. This is it's basically a disconnect switch device used to make or break a circuit at specified currents. Uh, they are equipped with auxiliary equipment to enhance the speed of the disconnect switch blade. Now, this is something that is not suitable for fault interruption. So only you can open this under load conditions. So this is basically if you are trying to isolate a particular segment of the feeder, these switches can be installed and they can be opened to break the circuit under normal operation. Next one is a circuit interrupter, a device designed to operate and close the circuit by non-automatic means and to open the circuit automatically at a predetermined overcurrent value without damage to the device when operating within its rating. So this is kind of similar to this is again a circuit, not a circuit interrupter, because a circuit interrupter is actually a more common terminology that can be used to include load break switch is a circuit interrupter in a sense. So, but this is something which is a manual thing, and or it could be automated at a predetermined overcurrent value. So, but it's not, again, does not have a fault capacity, fault carrying capacity, or fault interruption capacity, excuse me. Disconnecting switch is a mechanical device. It does not, the previous things that we talked about, they are kind of like you switch either electrically or some other mechanism that operates them. But this disconnect switch is pretty much kind of like a handle. You open the switch. So this is again, typically it is not used even load, normal loads you cannot break. It is more or less for dead circuits. So because many times you want to disconnect a part of the circuit for a maintenance purpose, so you de-energize the circuit and then you disconnect. But it does not have any other capacity. Sectionalizing switch allows breaking the feeder into multiple sections. Again, it does not have any other function except sectionalizing, and it is again similar to a load break switch you can consider, because it again does not have any fault clearing capacity, or only it can open under normal load situations. Again, keep in mind that the sectionalizer is a different from sectionalizing switch. Sectionalizer has a limited fault interruption capacities, but sectionalizing switch does not have any of that. Here is an example of distribution system where you have the substation right here, and then you have four feeders. There's a bus right here, and the four feeders coming out of it. These are voltage regulators to regulate the feeders voltages. So, and then you have four feeders coming out. Square boxes are circuit breakers, and then circles here, solid circles are sectionalizing switches. You got the simple switches, and then open or tie microgrid switch. So this is you can use this as an open switch, but they can be interconnected when needed. Now this particular picture also has a few microgrids. You have interconnection here to the microgrid. Again, there is a microgrid here. So they are kind of like whatever microgrid is here, there are four different microgrids, and in this situation, if you want to connect the microgrid to the grid, then you have to close the switch. Similarly, you have to close the switch. So this is just an example of a typical modern distribution system with some microgrids in it. And this is kind of like a not an actual really existing system, but it's a conceptual system. But there are a system similar to that in existence, actual existence. Not exactly the same, but similar. And of course, also notice that each of these feeders are operating in a radial mode, but they have a switch here. So we can you can do reconfiguration. For example, you can open this one and close this one, open this, close that. And there's so many different options over there. So the idea of putting these extra sectionalizing switches is to be able to get more flexibility in terms of reconfiguration of the system. And of course, same thing applies to the feeders right here at the end. This is open normally, but it can be closed in case of emergencies to reconfigure the system. So this has a lot of flexibility. So this is a conceptual. I don't think a real distribution system will have so many sectionalizing switches, but this is part of a project, so they are trying to show that by putting more sectionalizing switches, you can get more flexibility. There are very new generation of devices that are available with additional computing features and based on communication, so you can remotely reconfigure the devices. And many of these are actually still under development and not necessarily commercialized, but there are things that are happening, and in the future, it's an evolving process. So anything, every day, some new things are coming out, and these are some of the things that I'm going to talk about. So, for example, there is some movement to develop smart fuses. Now, the fuses that I talked to you about in the morning, they are actually dumb fuses. Dumb fuses in the sense that they just have a fuse, nothing else. But in addition to that, what people are trying to do is they are trying to embed some intelligence into the fuse by putting some monitoring components there. And they can, by doing that, they can implement current limiting, because if you put a monitor inside the fuse to monitor how much current is flowing, they can monitor the temperature and so many other things. So they are under kind of more like a research stage, maybe early stage of commercialization, but not very widely used. But there is at least there is some discussion and availability of these kind of fuses. Smart reclosers, again, reclosers are have seen pretty, they've been advanced pretty well. The two examples that I showed you are the two latest type of reclosers. So the old reclosers did not have any intelligence. They were pretty much local devices. Now you have Wi-Fi enabled electrical equipment inside the recloser, so you can communicate and you can kind of like set things remotely. Similarly, there are smart circuit breakers. Again, these are the things with wireless communication capabilities inside the circuit breaker, and those are again a new generation of devices that are being developed. In addition to that, we also have some new digital sensing and measuring devices. One of the most common ones people talk about is PMU, phasor measurement units. I think many of you must have heard about that. These are synchrophasors that are time synchronized to measure magnitude and phase angle at different locations in the system. And they provide accurate measurements of grid conditions because they are synchronized with respect to one another. So you know exactly what the phase angle is from one end to the other end. Otherwise, if you don't know that, you pretty much are estimating things and they are not very accurate. So they measure in things at a very fast rate, 100 times faster than SCADA. And then it is being deployed to a large extent in transmission systems to provide better visibility and provide higher stability to the system. So there's been deployed over the years, at least thinking about they came into existence about 30, 40 years ago, 30 years, roughly 30 years ago, commercialized 30, 35. And not overly widely used, but they are more and more being deployed in systems. And here is a picture of a phasor measurement unit. This almost looks like a relay. Same company that makes the relays also makes that PMU, and this is again a computer with fast measuring sensing capabilities, and then it also has communication to send information to other locations. Now, in addition to the PMU, there are also discussion about microphasor measurement units. So these are the PMU are pretty much for transmission systems. So people are talking about low cost PMU for a distribution system application. They are called micro PMUs, and they can be used in distribution systems at kind of like critical locations. And again, now PMU have been deployed quite a bit, but micro PMU is more at an experimental stage. You don't see a whole lot of deployment. These people just pretty much suggested, and some companies have developed them, but in terms of actual implementation, have not heard a whole lot, but at least it is available. And of course, microgrid, when they become more popular, micro PMU, because you have to synchronize things together, so I think they will have a lot of application. So here's the picture of a microphasor measurement unit. This is again a commercial equipment, and it is available in the market, but again, not being used a whole lot, but to a limited extent. In terms of other measurements, optical line current sensor. Now, typically we have current transformers that measure current. And you all know that current transformers are based on magnetic characteristics, and they have nonlinearities, and accuracy is sometimes not that great. So if you kind of think about it, that you want to use a PMU, which is very highly accurate in terms of measurements, and then you the input to the PMU is actually coming from the current transformer. So you already have put error in your measurements, because PMU cannot directly measure the current. It has to have a current transformer and a voltage transformer in between, and they have error. So if you want to increase the accuracy of PMU, you have to use sensors which are more accurate. So this optical sensing is an area where, again, this is something that at least I have heard about them for more than 30, 40 years. People have been talking about optical sensors, but again, the question is that when something is in an experimental stage and it comes to a point where the cost becomes compatible with what your existing equipment is, then people start thinking about it. But if it is for 20, 30 times more expensive, then people kind of wait and use it only on a limited basis. So they are becoming more popular, and they are available. The optical line sensors are available. We can buy them and install them. They can come as a three-phase unit or a single-phase unit. I don't have any picture of it, but if you search online, you may be able to find some pictures. Similar to current sensors, there are also optical voltage sensors that are available, and they again use optical technology to measure voltage, and they have significantly higher accuracy compared to voltage transformers. Although voltage transformers are pretty accurate, I think, unlike our current transformers are the ones that have more accuracy issues. In the same light, we have digital pressure and temperature sensors that can be used in a distribution system for protection because you are trying to, in some cases, you are trying to measure the pressure inside the transformer tank and you want to measure the temperature. Those are some of the things that are important to assess the state of the transformer, the health of the transformer. Okay? So in general, there is a lot of research still going on, development to build extremely high frequency, highly accurate devices, more accurate devices, because that way you can do a better job of protection. And some of these are such as extremely high frequency point of wave, dynamic high range sensors, optical PMU, and MaxSense should be considered for adoption as time passes on. So this point of wave is another approach where it's there's a different way of sensing frequency and voltage. I think this I won't go into too many details of that, but this is a conceptual thing where they can measure the voltage and current with high frequency waveforms very accurately. And then it's also possible that in the future we could have sensors based on nanotechnology. Because that's a topic which is also being researched quite a bit, and there is always a possibility. And then one could also expect some new materials, biomaterials could be developed for sensing and other things. So these are some futuristic things, and we can always expect something better to be available. So in general, if you think about the future, whatever we are doing right now may become obsolete in 10, 15 years. We don't know, because things are evolving so fast. The technology, you could have a lot of integration of AI in some of the decision making, and so at this point we don't know what the future is going to look like. But again, keep in mind that even though the technology may be available, the electric utility companies only will do things when they feel like, well, what we have right now is not working properly. They're not going to invest money just for the sake of it. They're not like us. We are very excited about new technology. You want to buy a new iPhone, you want to buy a new camera, you want to buy new things. But utility company always looks at the cost benefit. So although the technology might mature, but then there has to be a reason for them to change. Generally, electric utility companies have a lot of inertia. They're very slow to change. So how quickly things are going to change, we don't know. But in general, we expect them to change anyway. And another thing that will be something to watch for is an increased deployment of distributed energy resources in the distribution system. That is definitely going to happen and keep happening. Many of them will be based on IBR, which is inverter based, and they cause a lot of issues with respect to protection because they feed power in the reverse direction. And also, when the fault takes place, they have fault limiting capacity. So, this is again a topic which has many researchers working on to find out the best way to protect the system with IBR. So, again, if you are interested, I would say this is a topic which is very hot for people to consider, but very challenging topic. It's not easy. Okay, I think already talked about communication is going to be a big part of the future protection methodologies, and high power computing is again an important thing, and of course we can expect lot more integration of microgrids, and that will also throw in another challenge in the system. So these are some of the things to watch for. Okay, so this particular chapter is now done. So is there any question at this particular point before we move to the... Okay, so I can then close this one. Okay, so again, these are the introductory slides. Again, thanks to all the people who helped. Okay, so this is in this lecture. Now, the previous things we talked about, all these fancy devices, fuses, reclosers, relays, and everything. Now we're going to look at some applications to see some examples of how they can be used. So basically, as far as the coordination of devices is concerned, basically there are some basic rules for coordination, which is that anytime you have a fault in the system, the device that is closest to the fault should be the one that should operate. And again, accepting, like if you have temporary faults, they are taken care of by reclosing operation. But if the fault is a permanent fault, then it has to be cleared by some device. And the general rule is that the device that is closest to the fault should be the one that should open. Because if the device which is upstream opens, then you are unnecessarily taking out a larger portion of the system, and that's not desirable. So you want to disconnect that device which is the closest, so you have a minimum interruption. So that's the key thing. And then in general, in terms of terminology here, if you have two devices which are next to one another, and for example, in this particular case, you have a fuse here, one fuse, and there is another fuse here. So this particular arrangement has, and then there's a fuse here. So basically, you have a fuse, and then power is flowing from in this direction. So for a fault here, if there's a fault here, this fuse is the primary device because it's the closest to it. Now, for some reason, sometimes the devices may or may not operate properly because they are defective or whatever. So you have to provide a backup, because in protection you always have to have backup. So the fuse which is upstream here, this becomes the backup for this device. Similarly, this is also backup for the fuse here. But these two do not have any relationship because they are two separate branches. Okay? So what we have to make sure is that anytime a fault takes place, the selection of these two fuses has to be done in such a way that this fuse should get a chance to operate for all the possible faults. And if this doesn't operate, then we have to have a backup. Okay, so I'm going to show you some examples of that. And then in terms of these are kind of like general things that we already talked about over the course of our discussions. That is, I think these are some things that you can, these are kind of like approaches to put reclosers. We talked about fuses are normally used for taps serving single phase loads for short distances. Reclosers and sextilizers are utilized for large taps serving large loads for long distances. And then again, this is the same idea that we talked about, that for momentary interruptions, the recloser operates first and then lets the fuse operate later on. So I'm going to talk a little bit more detail. This is something that is there for you to read. And since we have already talked about them, we don't need to discuss them anymore. So anyway, this is again something that I already talked about, which is the aspect of coordination. That is, we need to select devices in such a way that they coordinate for all possible ranges of fault currents. And one thing you should keep in mind is that the selection of devices that is not an absolute thing. Like if multiple people are coming with an answer, they can have different answers, and it will still work. So, which is sometimes called art. It's not just science, but it's art and science of protection. So that is one thing that is very important. So when you are trying to do coordination of protection devices, what we need to do is we need to know a feeder configuration diagram, a topology of which way the feeders are going, where the devices are located, and we need to know mathematical models of protective devices, including their time current characteristics, expected range of normal load currents at all locations within the system, because we have to pick devices so that they don't trip when normal load is flowing. And then we need to know expected range of fault currents at all locations within the system. So before you can start doing protection, you have to gather this information. So you have to go through a full fault analysis with a table of faults at different locations. And generally, what we do is if we have to coordinate devices, we start from the lowest end, and then we move up in pairs. So you pick the device at the lowest end and determine its characteristics, and then go to the next level and pick that one to coordinate with the lower one, and then keep going. So that's the way the process works. It is a sequential process starting from load side up to the substation. And the key thing is that we need to keep a separation between the two devices, because these are time based. So all the devices have time inverse over current characteristics. So the separation between two devices which are next to one another there should be a minimum separation, because you need to account for allowance, because sometimes things are not very perfect, so you need to keep a sufficient gap between them. And of course, with digital devices, things have become, the tolerance can be a little bit tighter because they are more accurate in terms of their operation. The electromechanical devices used to be less accurate, so you have to keep larger margin. And this has to be, in case you have multiple the configurations of the system, the protection should work under all those conditions. So here is an example of, first we talk about fuse coordination. What happens if there are two fuses in series. So this is a graph of a fuse characteristics, and generally fuse will have, this is a 10K fuse. We talked about different types of fuses in the morning. This is a 10K fuse. A fuse will have two graphs with it. One is called the minimum melt time, and the other one is total catering time. The reason why we have the difference between the two curves is because it takes care of the age of the fuse, because if the fuse is new, has not seen any duty, it may take a little bit longer to operate. And a fuse is used multiple times, because what happens is that sometimes there is a overcurrent and fuse will start to become hot, but does not actually melt, and it cools again. But in that process, it may lose a little bit of its characteristics, so we have to allow for an allowance. So the lower curve is the minimum melt time, which means that it will operate in that condition even if it is an old fuse. Okay, so that's why fuse will always have two graphs associated with it. So the actual operating time can be anywhere in between. We don't know for sure. Okay? And again, sometimes actually people will allow another margin. So there is something called damaging time curve, which is approximately 75% of the minimum melt curve. So there will be, you take the values and drop down by 75% of those values, because again, this is to provide extra margin between two devices so they don't interfere with one another. Again, this is something that sometimes is useful to do that, because you don't know for sure what actually is happening, because some of the, in fact, even the fault calculations that you do in the system, they are not very accurate, because you are making a lot of assumptions. The model itself is an assumption, and then your actual fault currents may not be exactly the same as what you calculated at a location. So you can provide a little bit extra margin, because that way you can make sure that things don't miscoordinate with one another. Also, in a distribution system, we didn't cover the modeling part of it. The system, one of the challenges is to compute the line parameters, because you want to calculate the fault currents, you need impedance values of transmission or distribution lines. Now, in the transmission system, we assume that the three phases are transposed, but in distribution system, they are not transposed. So the impedance that you're going to calculate is going to be an approximation. So the fault currents that you're going to calculate will also be an approximation. So that's why putting an extra margin sometimes does not hurt. Now, as far as the fuse itself is concerned, a 10K fuse, actually, if you pay attention to it, this is right here is 20 amps. So the 10 amp, if a fuse that is rated 10K, the fuse actually will start to melt at 20 amperes. So 2 times the value. That's a normal process. Any fuse will melt at 2 times its value. Okay. So what do we, as a general rule, what we say is that we can pick a fuse which is rating must be greater than the full load value divided by 1.5. So a 10K fuse will be appropriate for full load less than 15 amperes, because this fuse is going to actually operate at 20 amps. So if the full load is 15 amps, it's not a problem, because you have 5 amp margin. So 1 point factor of 1.5 is to ensure that you still have enough margin. So that's how, based on the load current, we select the fuse. Now here is an example of two fuses. So basically what you do is you select a fuse for location B and you want to coordinate with fuse here. So we need to know the total clearing time of B and it should be, okay, let me think about it. The total clearing curve of B, which is the curve with, below A, B is below, A is above. So we have to look at the upper graph of B and lower graph of A. And they should be separated with respect to one another. And then generally acceptable method is that the total clearing time of B should not exceed 75% of the minimal melt time of A. So you could actually push A little bit if you want to, so by 75%, so you can get that margin that you're looking for. So as an example, let's consider a case where we have two fuses which are going to protect the system. We have a 40 amp is the load current here, 70 amp is the load current here, and of course there is another tap here, we don't need to worry about it. And in the circle what we see are the maximum and minimum fault currents which will happen on the downstream of the fuse. So 1794 and 1536 is the fault current here, and 1832 and 1581 are the fault current. Actually they are right here. Actually in fact the fault current here as well as there are not going to be very different from one another because this distance in the physical system is so small. It's only a few feet. So in practical sense, the fault current here and there does not change much or doesn't change at all. So this is the maximum and minimum fault current seen by this fuse, and these are the maximum and minimum fault current seen by this fuse. And this is a 12.47 kV circuit. So we're going to select fuse here as well as here for a load current of 40 amps and a load current of 70 amps, and we want to make sure that they coordinate with one another. So first step, we select the fuse links based on the specified full load. So for link location B, we divide 40 by 1.5 and that comes to 26.66. So we have to pick a fuse which will allow this much current to flow through it. And we similarly divide 70 by 1.5, so it gives you 46.66. And that basically gives us a fuse of 30T for location B, and it gives us a fuse of 50T for location A. Okay. Now, because the reason is that we computed 26.66 and 46.66, but the fuse don't come in all kind of rating. They come only at a fixed value. So the next higher fuse that is available, we pick that. So 26.66, the next higher is 30. So we have to pick that. So this gives you enough allowance between because a 30T fuse will start to melt at 60 amperes, 2 times the value, and the load current is 40. So you have a 20 amp margin between your maximum full load current and the point at which the fuse is going to melt. Okay. Similarly, for the fuse A, this you pick 50. So 50T will melt at 100 amps. The full load current is 70 amps, so you have a 30 amp margin. So that's how you select fuse. Now the next thing we want to do is we want to make sure that these two fuses are going to coordinate with one another for the given fault currents. So we draw the characteristics of both the fuses, and the top one is the 50T fuse with this is the total clearing, this is the minimum melt of melt time of the lower for 50 amp fuse, and for the 30T is right here. Now, what we want to make sure is that 1749, 94, excuse me, is the maximum current that this fuse is going to see, and also it will be seen by A. So 1794 is the current which is seen by both B as well as A. If the fault takes place right here, okay, then 1794 amps is going to flow in the circuit right here. So what we want to make sure is that at that current, the operating time between those two fuses is separated by a sufficient margin. So we go to the graphs here, and I think one thing I want to point out here is that there is a mistake in this one, because 1794 should be somewhere here, not there. And if you go back and look at this, what you will find is that at 1794, the minimum MMT is 0.05 seconds on the lower graph of the 50T fuse, and it is at that current the operating time of 30T fuse. Now 30T, keep in mind that you have to pick the upper graph of the lower end downstream fuse and the lower graph of the upstream fuse to find the time. And then we take the ratio of these two times, and that should be that we find, if you place this at the right location, 1794, you will find that the operating times are 0.037 seconds and 0.05 seconds for these two fuses. Then you take the ratio, it comes to 0.74. So we want that to be 0.75 because that's what is the margin that we want. So this selection is okay. It will work. Yeah. So make sure that there is this point, this vertical line should be shifted somewhere here, because this is 2000 is right here, 1000 is here, so the 2000, this should be somewhere here. Okay, now moving along, we have now we are looking at recloser fuse coordination, which is an important aspect. So in this case, what happens is that if you have a recloser here and a fuse here, the fault takes place here. Now the recloser has two graphs. One is the fast characteristic, other one is the slow one. So it's A and C. Now the fuse has its own characteristics, and typically the slope of the fuse does not match with the fuse slope of the recloser. So they intersect with one another. So the in between what you see here, this graph, there's a fuse right here and the two relay characteristics. So there are two intersection points A and B. And what we want to make sure is that these are obtained by minimum fault current and maximum fault current. And we want to make sure that under all conditions, the fuse and recloser coordinate with one another. And so in this case, what I will do is I'll show you some examples of how we select these devices, and want to give you specific examples of that. And of course, keep in mind that the recloser is going to operate first with using graph A 2 times, and then it will shift to C for 2 more. So it operates fast on the fast curve 2 times, and then it goes to slow curve for 2 times. Okay, so this is again some of the details that we already talked about. So let's go go to the next tab. I think we have already talked about those things. Okay. So, in general, finding A and B are very important because if you pick a smaller fuse, then the graph is going to move lower than where it is. If you pick a bigger fuse, it's going to move up. So both ways A and B are going to shift. So we have to pick the right kind of fuse which provides enough separation between their characteristics. Also, one other thing that is important to keep in mind is that all these devices are not very accurate. So we need to put some margin. So typically the recloser characteristics will have what they call a K factor, because although this is the declared characteristics for the recloser, they put an extra margin on top of it, and this depends on the different type of conditions. If you have too fast, too slow, one fast, too slow, those kind of things. So manufacturers typically provide a K factor, and that K factor has to be used to adjust the characteristics. Now, similarly, the fuse, the multiplying factor, if you have one fast instead of two fast, we can use a different 1.2 as a K factor. So depending on, again, the operating sequence, you have to use the K factor that the manufacturer is providing. And again, fuse has to be adjusted to 75% of its minimum melt characteristics. So you are pushing the recloser by a small factor, you're pushing the fuse by a small factor. So you have to work within that space to coordinate all these devices. And of course, the value of A is determined by the intersection of maximum clearing curve of the fuse with the slow characteristics of the recloser, right there. So this is the slow characteristic, and this is the maximum clearing curve, whereas this point right here is determined by the 75% of the minimal melt time and the fast curve adjusted by that K factor. So these are two important points to consider. Okay, now sometimes there is a fuse upstream of the recloser, because many times what happens is that you have a recloser, then you have a transformer, and on the upstream side there is another fuse. So that fuse also has to be coordinated with the recloser. So in that case, we also use multiplying factor of the recloser characteristics to coordinate with the fuse which is upstream. So the relay character, the recloser characteristics are multiplied by a K factor by moving it up by a little bit, and then put the fuse up there. So let me, in this table, that multiplying factor can range from 1.7 to 3.5. And this is again based on, these are the recommended coordination. This is for source side fuses, and depending on what the reclosing time is, anywhere from 25 seconds to 225 cycles to 600 cycles, 2 fast and 2 delayed sequences, 1 fast and 3 delayed sequences, 4 delayed sequences. So these are kind of like empirical values that the manufacturers provide, and these numbers came from Eaton Corporation, that is manufacturer of reclosers. And then this one is the K factor, which is for this is for load side fuses, and this one is for source side fuses. So both sides you have to have different numbers. Okay, so again, this based on, if the reclosing is faster, then use a bigger number. If the reclosing is slow in 60 cycles, 90 cycles, then this number is 1.25. And if you have only one fast operation, you can reduce that number by a little bit. So these are again because of some practical considerations. So here's an example we're going to look at. So here is an example of a system. We have 46 kilovolts system here, and then on the low side it's 12.47 kilovolts. This is the 46 kilovolts line to line delta side. 12.47, 7.2, 7.2 is line to neutral. 12.47 is line to line. Delta Y grounded transformer. There's a fuse on the primary side. There's a recloser here, and then there is a fuse here. There's a fuse here, and these are the maximum in the circles, the maximum and minimum fault currents at these locations. Okay, so similarly here, bus 3, 1610, 680, 1630, 690. 80 amps is the load current, 150 amps is the load current here, and again these are the fault current values. These are fault current values. So what we want to do is we want to select the all these things. We want to select the recloser, we want to select the fuse here, we want to select the fuse here, we want to select the fuse here. That's the problem. Okay, so I'm going to show you some calculations on how to do that. And we go step by step, and we'll make sure that we select all the equipment that will provide us proper coordination based on the rules that we have already talked about. So we're going to consider all of those. Okay, so first of all, we will select the recloser. That's the first thing. We're going to select this recloser, and it has load current of 270 amps. Okay, maximum load current of 270 amps. So we want to pick a recloser that will provide protection for that current. So the reclosers that are available, type L, this is again a designation of the manufacturer. They call it type L, and they have different pickup values. Like they have ratings, trip coil ratings, different values, and they provide characteristics for those ratings. So 280 is one of the ratings that is available. So which is rating is close enough to the load current of 280, which means that the trip coil will operate at 280, which is higher than the load current. So we pick the current, this one. The trip coil recloser will trip coil rating of 280, and 4000 amp is its fault interrupting capacity. So that's higher than 3000. 3000 is the maximum fault current. So this recloser with 280 amp trip coil and 4000 amps interrupting capacity is good for this location. Okay. Now the next thing we want to do is to select this fuse. Okay, now this fuse has to be selected in such a way that for maximum fault current of 3000 amps, the fuse should not interfere with the recloser. So it means for all for at 3000 amps, the fuse should be delayed enough above the recloser. Okay, so we want to pick that. So what are the rules here? Now because we have a delta Y transformer, the fault current that is 3000 amps will not, if you have 3000 amps here, the 3000 amps will become a different value on the high voltage side. Now, for a three-phase fault, the currents will directly convert in the ratio of the voltage ratings, line-to-line voltage rating. But for other types of fault like single line to ground and line-to-line fault, the ratio changes. And there are some calculations that are available that allow you to do that. So what we have to do is we have to choose the worst case. And what we find is that if you look at the ratio between the primary current to the secondary current, for three-phase fault, it is in direct proportion to the ratio of the number of voltage ratio. And for phase to ground fault, this becomes 3.2. And for line to ground fault, it becomes 6.4. So this is the most critical situation because that creates the minimum margin. So we have to consider line-to-line fault as a critical part of our coordination. So we will use this 3.2 factor of 3.2 for our calculation. Okay. So then what we do is we go back and look at the fuse that we need. And so 270 amps, which is the load current, is going to become 73 amps on the primary side because of the factor 3.7. Okay. And then we use the same rule, 1.5 rule for fuse selection. So based on 73, we divide that by 1.5 and then we come up with a fuse which is 65 E fuse. Okay. And then this fuse can carry up to 97 amp of continuous current, and this particular fuse is okay for the location. So we use the same idea and we come up with this fuse because 65 E fuse will be able to will melt only at 130 amps, the double that. So this is suitable for this location. So we pick that, and then as far as the recloser is concerned, we have to multiply. We are considering two fast and two slow operations. So we go back to the table that was given to us by the manufacturer. They say we need to multiply the characteristics, the slow characteristic by a factor of 1.7. So we're going to use a K factor of 1.7. And then we will plot these characteristics, the recloser characteristics and the fuse characteristic that we selected on the same graph and then see what happens. So we plot the fuse here. So this is our recloser A curve. This is, you can see, if you can see that, this is, let's see, where is the, okay, this is recloser A curve of the recloser. This is our 65 E fuse. But 65 E fuse has to be multiplied by 3.2. So this is the 3-point fuse characteristics have to be scaled up because we are trying to, because the voltage change, when you draw the graph, you have to make the adjustment because you are looking at the fuse being on the high side. So for the fuse to blow, you have to have higher current on the low side. Okay, because that whatever the melting current is has to be seen based on the primary side because the recloser characteristics are drawn based on the low voltage side. So the recloser, the fuse characteristics have to be brought to the low voltage side. So that's done by multiplying. Now here we also see this is the recloser C curve, which is the slow curve. Okay, and then we multiply that by 1.7. So this becomes the recloser characteristics. Okay, so we put all these things together and we find that the minimum melt characteristics of the fuse of 65E and the modified curve of the recloser is found to intersect at about 1800 amps. So basically, right here is the intersection between the two of them, right there. Okay? This is the modified characteristics of the fuse. This is the modified characteristics of the recloser. We find that they intersect at 1800 amps. So we have a problem, because if you go back and look at your data, what we want is we want the coordination to be at the maximum fault current, and the maximum fault current is 3000 amps. So basically what is going to happen is that at 3000 amps, which is right here, the fuse is going to blow before the recloser. That's miscoordination. Fuse should not blow before the recloser. Recloser should be the one that should operate. So this fuse is going to cause miscoordination. So this is not acceptable. So what we have to do is we have to go to the next higher fuse. 65E is too small for that. So we pick the next one, which is the shown here 125E. And this fuse is bigger, 125E, and that's the one right here. And you can see that at 3000 amperes, we have significant margin between the recloser characteristics and the fuse. So we will get proper coordination without any problem. Okay? So that is the coordination of the recloser with the fuse on the upper side. Now we're going to move to the coordination to the load side. So this is actually the same graph drawn again with all the details that I told you. So at 3000 amps, we have sufficient separation between them, so it's okay. Now we want to select the fuse F1 and F2 to coordinate with the recloser. Now we already have picked our fuse at the right here. Is okay, it's done. We have the recloser. Now we want to pick the fuse here and this fuse so we can get proper coordination. So let's move on. Okay, so again we use the same logic, and the load current for F1 and F2 are 80 and 150. And then again, using that factor of 1.5, we come up with 65T for 80 amp line, and then we come up with 100T for the other line. Okay, so we have the two fuses. F1 is 65T, F2 is 100T. And again, like the slow curve, a K factor must be applied to the recloser fast curve, and that K factor of 1.3 can be found from the table. So we use 1.35 for two fast operations, and we are assuming that the reclosing time is 60 cycles. So we use that. And then we will put these graphs on right here. And again, notice that we have this is the fast curve of the recloser multiplied by 1.35, because we have to push that up. And the fuse characteristics are shown here. This is the recloser C curve of the recloser, and then we have the 65T fuse here and 100T fuse here, and also I have included an 80T fuse in between. And what we have to do is we have to have the coordination between these devices at 680 amps, 690 amps. Those are the minimum currents, fault currents that are going to flow on the lines between, if the fault happens here, for example, 680 amps are going to flow in the circuit like that. Fault happens here, 690 amps is going to flow here. But if the fault happens to be here, right here, then it's going to create a fault current of 2380 amps. That's the maximum current. So the recloser and the fuses have to coordinate with one another for a fault current of 230 amps maximum and 680, 690 amp. Those are the minimum currents. Okay. So what we are going to do is we are going to use these currents to make sure that we have a proper coordination. So go to the next slide here, and what we find is that we already selected the fuses, and then we draw the plots here, and what we find is that the 680 and 2380 are the critical times. So F1 and F2 MMT should be higher than 0.505 seconds for a current of 2380 amps. So at 2380, which is, this is 2000, so 2380 will be somewhere right here. And what we find is that curve A of the recloser times 1.35, which is this graph right here, and 80T and 100T at 2380, 65T fuse is too close to the recloser characteristics. 60, 80 and 100T are okay because they have enough clearance. But 65T is, there is hardly, they are touching almost at 2380. So we don't have enough clearance. So 65T is not going to work. As far as the 680 and 690 amps are concerned, which are right here, 100, 200, 300, 400, 500, 600, 700, right there, we have plenty of space between the recloser and the fuse characteristics, so we are okay. So the lower limit we are fine, upper limit we have a problem. So 65T cannot work. Now we go to the other side, because now the fuse is okay with the slow curve, with the fast curve, but it also has to coordinate with the slow curve. So in that case, what we want is that F1 and F2 maximum clearing MCT, which is maximum clearing time, right here, should be lower than 0.3 seconds at a current of 2380, because what we see here is that 2380, this is 2000, this is recloser curve C, and we see that all three fuses, there is plenty of gap here, so there is no problem. Okay? But when we come to the lower end of this, what we find is that at F1 and F2, which is 690, right here, 100, 300, 400, 500, 600, 700, 65 and 80 are okay. 100 is too high, and it's going to interfere with the slow curve of the recloser. So what is happening here is that the 65T is interfering with the fast curve, and 100T is interfering with the slow curve. So both 65 and 100 are going to give you a problem. So what we have to do is we have to compromise and pick 80T as the fuse for both locations. So 80T will work. The only drawback is that 80T, the analysis indicates that only fuse that satisfies all the requirements is the 80T fuse. Although the desired fuse for F1 was 65T, it needs to be increased to 80T to ensure adequate protection, because 60T is too fast. It interferes with the recloser. And F2, the desired fuse for F2 was 100T, but it needs to be reduced to 80T for proper coordination of the recloser with the recloser. So it is important to note that 80T fuse will coordinate with the recloser, but it may melt under maximum loading conditions. So you have reduced the loading capacity. Instead of the higher value that we have to reduce it. So this is an example of by how you coordinate the fuse at the upper end and fuse at the lower end, so that you can get proper coordination for temporary faults as well as permanent faults. Okay. So let me move to the next few things. I think we have about 20 minutes or something. हाँ 20 मिनट है ना करीब 20 मिनट है अच्छा okay so this one is an example of coordinating a recloser with a sectionalizer.
Yeah. Regarding the selection of fuses, you are saying about 80T, 60T. So is it the setting for timing, limit or range?
What is that again?
80T, 100T you are saying, sir. For the fuse ratings. Yes. So for the fuse ratings, the current is given for 680 amps, there is 100T. So what is that, how you are correcting that 680T for 600 amps? Is it some rating? T is something which I did not understand, sir.
No. The thing is that we have two fuses that we decided to select based on the ratings.
What does T mean, sir?
T is the type of fuse. T is type of fuse. 65 is the rating, T is the type of fuse.
Yeah, for fast switching, it has different T. Or can...
No. This is actually based on when we talked about different type of fuses. You have T-type fuse, you have K-type fuse.
Okay.
So one of those, you could try to apply a different kind of fuse if you want to, and the answer may turn out to be different. But in this case, I give you an example of using T-type fuse. So T is just the designation which is based on the characteristics of the fuse. Okay? So in this case, we are going to look at recloser sectionalizer coordination. And again, this is something that we have already talked about, because in this case, what happens is that you have a recloser and you have sectionalizer. A recloser is designed to operate, have 4 trips, too fast, too slow. Sectionalizer will have 3 counts, and then again, it will count the number of times the recloser operated, and after the 3rd operation, it's going to open. And then, of course, typically the actuating current of the sectionalizer is set to 80% of the recloser's minimum trip rating. So if this one has 100 amp trip rating, this will be set to operate at 80 amps. Just some kind of a general rule. Okay, now what we want to do is we want to look at circuit breaker recloser coordination. Okay, and in this case, the circuit breaker does not have its own protection mechanism, so relay is used to operate a circuit breaker. So we're going to assume that the relay is going to be based on a L08 relay with the characteristics shown here. And again, the rules for coordination are the relay time current characteristics of the circuit breaker should be set above the characteristics of the primary device. The pickup of and time dial setting of the relay should provide sufficient safety margin with the selected characteristics of the recloser or other devices. And the instantaneous relay characteristics should have a proper safety margin above the fast curves of the recloser or other devices. So recloser has a fast curve, and if the circuit breaker has an instantaneous relay, the instantaneous relay should be above the fast curve, because the recloser is the one that should have the first option to operate. Because if your breaker is going to operate before the recloser, then you have miscoordination. So anyway, I think I'm going to, these are some rules for coordination. Let me go ahead and show you an example. So we have a recloser here we have circuit breaker here, and again these are maximum minimum fault current that are given, and 185 amps and 110 amps, these are the load currents, and we are going to look at coordination. So the first step is to select a recloser. Since the full load current is 110 amps, a recloser with 140 amp trip coil setting is appropriate. This shows the recloser curve A, and it also shows recloser curve C. So A and C curves are shown, and then we want to select a CO8 relay for the circuit breaker. Now for a load current of 185 amps, 200 to 5 CT will work. So further we select 5 amps as the tap setting for the relay, because that will allow some margin for overload on the feeder. And then in the next step, we will we have to select the time dial, and time dial has to coordinate. Now these two things have to coordinate for a maximum fault current of 1832. Because 1832 is the fault current seen by the recloser as well as the circuit breaker. So this becomes 1832 becomes the critical current for coordination. Always the maximum current, common current seen by both relays should be used for coordination. And using that, we will now, okay, let's move forward. So we use 1832, and we will compute again using this formula. MTS is equal to I fault, which is 1832. CT ratio is 200 to 5. Tap setting is 5. So this gives you multiple of tap setting. And for that CO8 relay with 9.16, we will use that. And of course, this is the CO8 setting with a time dial of 8. We select that, and we draw the relay characteristics, which is right here. And the critical current that we are looking for is 1832. So at 1832 amps, the recloser takes 0.24 seconds to operate on the slow curve right here, right? This is the point right there. So we want to find out what is the difference between the two. And we, if we look at CO8 with time dial of 8, it takes 0.3 seconds. So the relay takes 0.3 seconds, and the recloser takes 0.24 seconds. So 0.06 seconds is the separation between the two of them, which is acceptable. But if you want to add extra delay, then you have to pick a higher time dial. The time dial in the new digital relays, you can pick fractional numbers like 8.1, 8.2, 8.3. So you can increase it by a little bit if you want to put more spacing. But in old mechanical relays, we had to pick integer 1.5. I think it was in increments of 1/2 that you had to use. And so this shows that we can use coordination between, first you select the recloser and then you select proper relay. And the main thing is that the relay characteristics have to be selected in such a way that they coordinate with the recloser. So always the key thing is that for maximum fault currents, the device that is upstream should allow, there should be a gap between the operation time of the device that is downstream and the one that is upstream. And because otherwise, if the upstream device operates faster than the downstream device, you get miscoordination. Okay, so that is all we have, and now I'm open to questions. How much time we have? 10 minutes? Oh, there's plenty of time.
Option
It's easier for you to understand.
whether to choose a fuse rating for 65E or
65T or 65K, is it completely dependent on me or the condition that will face?
Is it dependent on?
We that are choosing means we for a 65E can be equal to a higher version of say 80T like.
No. It's not that. Let me. Okay, we chose 65T and 80T, 65T because okay, the load is specified to be 80 amps and 150 amps. So you have to pick a fuse to allow 80 amps of current to flow on the line. Okay, so the rule is that you divide 80 by 1.5, it gives you a number which is 53.
That is for T type fuses.
Any fuse.
Okay, any fuse.
This rule applies, 1.5 rule applies to every kind of fuse. So you can choose, you divide 80 by 1.5, it comes to 53, and 150 divided by 1.5 gives you 100. So basically what you are doing is you are dividing the maximum current, the load current that is given to you by 1.5, you come up with a number and choose the fuse which is available that is next higher in terms of its rating. So what it means is that this 60 amp fuse, which is the next higher available, will up to 120 amps, it's not going to melt. It's going to start melting at 120. And your load is 80 amps, so you have a margin of 40 amp fuse.
Okay, so the current rating and the fuse type, they are completely unrelated.
What is that again?
And the current rating and the fuse type like K type, E type, these are completely unrelated.
No, the K type, T type is actually, let me go back to let me select the slides. Okay, so I think this was in the previous presentation, I think. So lecture 7. Okay. So this is these are the graphs of what happened? Okay. So this is the type T fuse right there. These are actually all the fuses are 25 ampere fuses, but you have 25N, 25K, 25T, 25S. So the difference between them is that if you pick a fuse, 25N is a faster fuse. Because for the same current, it's a 200 amps current, now 25, all of them will approximately, this is like 50 amps is right here. So these fuses will, except for 25N, there is, it's like this is 50 amps here. So this one, I think they go a little bit higher than that. But anyway, what you see is that N fuse is the faster of all of them. K is the next, T is the next, and S is the slow one. So you can pick any fuse you want. These are the characteristics that the manufacturer is giving you. Okay, so you pick S or T, it doesn't matter. What you're trying to do is, I gave you an example of using T-type fuses. You could work the same example with K-type fuses. It doesn't matter.
Okay, sir. Thank you.
Now, 65, that number is essentially means that that's the rating of the fuse. And in general, except for the N-type, K-type, T and S, there you can see that they converge at that point, which is the 50 amp. So any fuse, as a general rule, will start to melt at 2 times its rating. So if you pick at 50T, 50T will melt at 100 amps. 60T will melt at 120 amps, the minimum melt. Question?
For modeling and simulation of hello. So for modeling and simulation of power systems, which is a better software, MATLAB or PSCAD? Or
For
any
different applications, you use different software. It depends. There are so many of them. There is PSCAD, there is Mat Power is there, and then Power World, ETAP. There are so many of them. I don't have a particular preference, just up to the different applications.
okay.
We use Power World for our power system analysis class, and we use ETAP for protection class.
Okay.
And then as far as the research part is concerned, it's so many different things. I think most of the students use MATLAB.
Yes. Sir. Okay. Thank you, sir.
Yeah. But for protection purposes, ETAP is really good. They have a lot of features. You can draw the fuse library of fuses. You can pick any kind of fuse. They have reclosers. They have different type of relays, and you can draw all these coordination graphs without any problem. I know that when I studied protection, which was long time ago, we didn't have computers in those days. So we had to draw these graphs by hand. In fact, even until about 2000, 95, 2000, the class I used to teach, they had to draw graphs by hand. So what you have is relay characteristics on a sheet of paper. It's like a graph, printed graph. And then go to the bookstore, and they used to sell relay log graph paper specifically designed for relay coordination. And then you get the drafting table and put a light underneath, and you trace the graphs by hand. And I have done that, my students have done that, but now it's all based on computer. You can use the computer to do it. So ETAP is good, it has all the features. For research purposes, I think some of these softwares are not that good because you have a lot of constraints. You cannot write your own code. So you have to depend on, like, you can use it as a module to test your results, but you cannot actually do any kind of, they don't have flexibility for research purposes. That's what it is.
Sir, my question is that regarding the K-factor selection,
Yeah.
is it dependent upon the fuse type or the requirement for us?
It
Regarding the application.
doesn't depend on the fuse type. It depends on the operational count. How many times you, like, if you look at the table, if you have one fast and two slow, one fast, three slow, two fast, two slow. So the recloser, how you set your recloser, that determines the K factor. Fuse is independent of that. Now these K factors are actually, again, these are empirical values. We don't have any way to test them because the manufacturer is giving these numbers to you. So you have to kind of, these are kind of like margins of safety that they are providing. And again, the question is that these numbers are based on old technology, the new technology, these numbers may be different. But I included these numbers because Eaton, which is the manufacturer of reclosers, they have a kind of like a manual and these numbers are listed in that. So this is a suggested guide. It's not like 100% gospel that we have to follow it, but it's kind of like a suggested thing. Because this protection is a very subjective thing. Some people are willing to take more risk, so they may use. You may say, okay, forget about K factor. I'm willing to take the risk. Some other people say, no, I want to have more gap between devices. So they say, okay, I'm going to spread the characteristics a little bit by putting extra margin. So this is just a way to kind of assure yourself that you put enough margin in the system. If you don't use K factor, still things may be okay, but you are pushing things a little bit close to the margin. You've done. Oh, if your time is up, we can. It depends. Who get time pura? ठीक है. That's okay. All right. That's great.